Good morning, students. Today we are going to see what a regenerative cycle is about. What are the advantages of this cycle? We know that the Rankine cycle is an ideal cycle for comparing the performance of steam plants. So in the drawing you see a schematic diagram of a turbine plant is given. Here this is the boiler. Heat is supplied in the boiler to the water, and the water is converted to steam. So this 1 to 2 is the process what is going on inside the boiler. The heat supplied at constant temperature. Steam is entering the steam turbine here. It is expanded in the turbine. 2 to 3 is the process of isentropic expansion. The work output is taken from the steam turbine here. Here from 3 to 4 it is the condensation process. Here also it is condensed at constant temperature, and from 4 through the extraction pump the condensate is taken to the hot well, and from hot well it is pumped into the boiler using a feed pump located here. So the Rankine cycle, it has got one is the isothermal expansion, then isentropic expansion, you got isothermal compression. These processes are there. Then what is regenerative cycle? Now see, you can see this diagram here. Regenerative cycle using a single feed water heater, the regeneration is done. It is nothing but, see, the feed pump is supplying feed water into the boiler. From the boiler steam is taken to drive the turbine. In the earlier case, after all stages the steam is left out, the exhaust steam is drawn out and condensed and sent to boiler. Here somewhere in between steam is bled, part of steam is bled. Let us say here 1 kg of steam is entering here in the first stage, but in between m kg of steam is bled, and it is used to, the heat energy of this bled steam is used to heat the feed water which is coming out. See, after driving the turbine, which is the feed water is from the condensate, from the condenser, that is now it is heated here. The feed water is heated using the blood steam. So this feed water which is heated as well as the steam after giving its heat to the feed water, that is condensed, both are mixed together, and that is drawn by the feed pump and it is supplied to the boiler. So by doing so, what we are trying to achieve. One is that this process increases the thermodynamic efficiency of the turbine. That is one thing. Second thing is that the boiler is supplied with a hot water. Earlier, straight away the condensate from the condenser was supplied into the boiler. So that must be at a lower temperature. But now here, this condensate is heated using the steam blood from the turbine somewhere in between, and the mixed one. That means the blood steam also is condensed. The feed water temperature also is raised. Both are mixed together and it is sent to the boiler. So effectively, the boiler is supplied with a hot water. So the thermal stress will not be there in the boiler. That is one advantage. Thermal shock won't be there. So another advantage, as I already mentioned, it increases the thermodynamic efficiency of the turbine. For these two reasons, the regenerative cycle is employed. Here in the diagram, what you see is only a single feed water heater. It is given as open feed water heater. Open feed water heater means both are mixed. The steam, blood steam as well as the feed water, both are mixed together. Generally in the heaters you will find the steam and the coolant, they will not mix together. They are two different media. But here it is mixed together. That is why it is called as open feed water heater. So here 1 kg of steam at enthalpy H1 is entering the turbine, and at B, m kg of steam is bled, which is at an enthalpy of H2, and in the final stage you will find, so 1 minus m kg of steam, the exhaust steam at enthalpy H3 is going into the condenser. So 1 kg is entering at point A, m kg is leaving at point B, 1 minus m kg is leaving at point C. So 1 minus m is coming in this side. So this H3 is the exhaust steam enthalpy, the final stage. So after it is condensed, HF3 is the enthalpy, fluid enthalpy of the condensate. This enthalpy HF3 is increased by the blood steam, which is coming at an enthalpy H2. So we are getting an enthalpy of HF2 here. So it is a 1 kg, because m kg is entering here, 1 minus m kg is coming here, m plus 1 minus m, the final one is 1 kg at enthalpy of HF2 is getting into the feed water. Here what we see for our calculation purpose, we can see here heat lost by blood steam. What is the heat lost by the blood steam? That is heat gained by the feed water. Okay, so heat lost by blood steam is how much? M kg of blood steam multiplied by H2 minus HF2, that is equal to 1 minus m kg of feed water multiplied by how much is the heat gained by the feed water? HF2 minus HF3. Okay, that is MH2 minus MHF2, that is equal to HF2 minus HF3 minus MHF2 plus MHF3. Okay, if you simplify this one, what you get? M is equal to HF2 minus HF3 divided by H2 minus HF3. HF2 is here, HF2 minus HF3 divided by H2 is here H2 minus HF3. This is the M. If you want to find out the blood stream quantity, that is nothing but HF2 minus HF3 divided by H2 minus HF3. Coming to the work done in the turbine per kg of feed water between A and B, because between A and B, 1 kg of steam is doing the job. So how much is there? Enthalpy lost, H1 minus H2. So work done in the turbine per kg of feed water between A and B is 1 multiplied by H1 minus H2. Work done in the turbine between B and C. You can see between B and C, how much is the work done? Here mkg is leaving. So what is going from B to C? It is only 1 minus mkg. 1 minus m multiplied by H2 minus H3. So that is the work done in the turbine. Work done in the turbine between B and C. So between A and B, H1 minus H2 is the work done. Between B and C, it is 1 minus m into H2 minus H3. What is the total work done? The total work done is adding both these together. Total heat supplied per kg of feed water. How much is the total heat supplied? It is H1 minus HF2. H1 is the enthalpy here when the steam is leaving the boiler, and what is the enthalpy of the feed water? That is HF2. So H1 minus HF2 is the total heat supplied per kg of feed water. Then what is the efficiency? You know, efficiency is total work done divided by total heat supplied. So we'll get the efficiency. In this case, how the temperature entropy diagram is to be drawn, you can see here. This is a temperature entropy diagram. You very well know in a Rankine cycle, the exhaust steam is condensed up to the saturation liquid line. Okay, that is what is happening here. So this is a temperature entropy diagram. This is a saturated liquid line and this is a saturated vapor line. Here 1 to 2, what is shown here is it is not corresponding to that one, but the diagram, schematic diagram here, 1 to 2 is nothing but it is 1 stands for A point, 2 stands for B point, 3 stands for C point. So this is 1 to 3 is nothing but the expansion process, isentropic expansion process which is going on in the turbine. Okay, 1 kg of steam is entering the turbine here at point B. This 2 means is a point B as shown in the schematic diagram. mkg is leaving the turbine. mkg. It is for heating the feed water. And here, final stage, if mkg is leaving here out of 1 kg, then 1 minus m is leaving the exhaust stage and it is going and pumped to the boiler and heated and coming to the turbine here. Okay, so this is how you have to draw the TS diagram. Here only once from only one place only the steam is bled, but in actual scenario you will find at 5-6 places steam is bled at different pressures. So you will have many heaters, feed water heaters. Here only one feed water heater is shown. So these, every feed water heater, that will operate at different pressure. So the steam is drawn from different stages of a turbine. One will be at maybe 10 kg, another might be at 5 kg. Likewise, from different stages and different pressures, steam is bled to increase the feed water temperature. Here only one stage is given. I hope this is this by this you should have understood regenerative cycle. And in the problem, what would be given, you would be given the point A, point C, and you might be asked to find out what is the quantity of blood stream. So you can use this formula. And the effects of bleeding, as I already mentioned, one is it increases the thermodynamic efficiency of the turbine. Second one is the boiler is supplied with the hot water. By supplying the boiler, which is maintained at a higher temperature with a hot water, thermal shock is prevented. Another effect of bleeding is a small amount of work is lost by the turbine, which decreases the power developed, because you are drawing pot of steam. You are not allowing the complete steam, 1 kg of steam, to pass through the entire stage of the turbine. Pot of steam is being drawn for heating the feed water. Definitely we will lose some amount of power developed. Okay, that's all. If you have got any doubt, you can write in our WhatsApp group. Thank you. Bye.